It's a great pleasure for us to have with us Efi Tsompopoulou and Antonis Nikitakis of deepSea, a very active and productive new company. And I'm really eager to hear what you've been doing with AI. Thank you for accepting our invitation, and please try to keep your presentation to about 30 minutes so that we can have some discussion, if possible.
Great. Hello to everyone. It's a pleasure being here today to share some interesting concepts and ideas we have been working lately at deepSea. The title of this presentation is Towards Trustworthy AI Models for Shipping. We would like to share some the problems we're facing with AI effort, but also we want to sit back a little bit and reflect on a more general topic, which has to do with trust in AI, because we believe that is something that all the industries at this moment are facing. So throughout this presentation, we would like to also see what we're facing through this lens. Before moving to this discussion, a few words about what we are doing in deepSea, what products we offer at the moment. So we have two main products. We have Cassandra and deepSea. Cassandra focuses on how to monitor a vessel's performance, and we're doing so by modeling all the various machinery of the vessel, such as the hull, the main engine, and the generator engines. So we model all those aspects, and by the predictions our models are giving, we enable our users to optimize the performance in all of those aspects. In deepSea, on the other hand, we're focusing on the voyages. So the user, by defining the departure point, the destination point, given ETA and some other constraints, there we suggest an optimal route on how you sail from point A to point B, and minimizing the fuel consumption and emissions. As you already understand, both of our models are powered by AI, so they're heavily dependent on vessel-specific models, as we say. So we build a separate model for each of our vessels, and such model is it's purely data-driven. So it uses only the available data of this vessel. So it's really important that we need to have trustworthy and accurate models. Really important to assure that our products, since they are decision-making product, decision support products, they have to operate at any given circumstance. So moving on to speak a little bit about the challenges we're facing in shipping, but most of them also we think are the same for other industries. So since we're purely data-driven, all data-related issues, they directly reflect on our models. And one of the most prominent of such an issue is distributional shift. This is a broad term, and specifically for us, it refers to observing that our data distribution is shifting over time, and this is because we have some latent phenomena going on. Latent means that we cannot directly measure them. For example, we have hull fouling. Hull fouling is when under the surface of the vessel, bioorganisms are growing, and as a result, they affect the performance of the vessel, essentially the friction between the vessel and the water. And although we cannot directly measure this, we have somehow to track it through time, to model it, and also to make predictions and estimations about it. We also have various data drifts or sensor drifts, as we call them. So our sensors, they may be miscalibrated, and they themselves, they cause also this distributional shift. Of course, we have biases in our data sets. The most common is a sort of selection bias. And this happens because the operators of the vessel, they choose to operate it they prefer to operate in certain conditions over other conditions. It's a very reasonable thing to do. So this infuses spurious correlations within the data. And as a result, these correlations, they may affect the models. Of course, we have states in a data set that are underrepresented, also because of this selection bias process we have. And of course, we have noisy data, corrupted data. We have lots of outliers that we have to handle, reject them, and make sure that they not affect our models. At the same time, while we are trying to address all those known issues, I would say, we have to gain our stakeholders' trust. We have to somehow assure that we are addressing them in an effective way, but we also have to prove that we're doing so, and we are sure that our models are going to perform at any given circumstance. So the question we put here is, are the common evaluation accuracy metrics that we use, we share across the literature, are adequate to measure how good a model is, and basically to enable, to promote this trust about AI. Yes, this is an open question, basically. We don't think that we are there yet as a scientific community, but we think we have to focus more on explainability. So it's really important not only to focus on how we improve our methods, but also how we make our methods more transparent and more explainable, because it's really essential for the user, for people, for humans in general, to be able to trust AI. So a few words about what are the goals of explainable AI. So two very known terms are interpretability and explainability. First and foremost, there is no solid definition here. The terminology is a little bit fluid at the moment. So interpretability in general refers to how we determine cause and effect from a model's prediction. So in other words, how we can attribute to some cause a certain model prediction, or in simpler words, how we make sense of a model. So we have to somehow to understand that a model makes reasonable predictions. Explainability, on the other hand, focuses more on how the mechanics of the model, how the model is working, can be explained in human terms. So explainability is really important on how we communicate as humans between us, how a model basically works. And some of the major goals that explainable AI tries to address, especially in this industry. We already touched upon trust. This is the holy grail, the goal, the main goal. We also have transferability. We have somehow to assure that by transferring the model from environment to environment, the model still works as it should. Specifically in deepSea, we're using knowledge transfer methods. So we may transfer a model from one vessel to another and then adapt it to its specific data. And we have to assure that the model still maintains all the necessary properties and performance. Of course, causality is really key because we are building decision-making systems. Our models have to assure causality, and of course we know that machine learning methods, data-driven methods, are inherently correlation methods, but there are still things we can do to assure that we're building causal models, and also to develop methods of evaluation methods that also can assure that we're having this performance in place. We also have fairness and ethical goals here. We have compliance and ethical standards that we have to assure that we are compliant with. And I would say that ethics and explainability are almost they have almost 100% overlap, where I cannot even imagine how a model could be ethical if it's not explainable, because ethics and fairness are properties that cannot easily measure. We're even having difficulty to define them properly. So it's really key here to have transparent and explainable models. And finally, informativeness refers to how rich is the information that the model passes to other tasks and systems. So we're building AI models because we want to build something bigger. We want to build something upon it. An example in deepSea is deepSea. deepSea runs sophisticated optimization algorithms, and those algorithms are fed from deep learning models. So the information that those models they pass to those algorithms, it has to be robust and reliable, and also rich enough to solve the task. So this is really important. And later on in this presentation, we will speak a little bit about modeling uncertainty, which is an additional information we can pass to those downstream tasks to help them operate better, let's say. I think that is for me for now. So I will stop here and pass the presentation to Efi, and of course I will join later on with the questions and the discussion. Thank you.
Thank you, Antonis. So yes, now we are going to move on, discussing stuff like a methodology that we have developed and the techniques that we are using in order to address the challenges that we are facing in the shipping domain. So we will cover three main concepts. But before that, let's begin by discussing how a typical machine learning pipeline looks like in our case. So the first step in the pipeline is, of course, the data. Here we are working with time series data with a per minute granularity. We have signals coming from multiple sources, like onboard sensors, the GPS, and weather providers. And we have our preprocessing process where we try to clean the data in order to end up with the records that are going to be used for the training step of the models. So the next step is the modeling. Here we're working for a regression task. Particularly, we want a model to predict the power or the fuel consumption of a vessel for all possible operational and weather conditions. Of course, a very important next step is the evaluation of the performance of the model. So here we use, of course, the standard performance metrics, but we also perform some simulations of what-if scenarios in order to explore the behavior of the model in the different regions of the feature space. Once we are satisfied with the model, then we transfer it to the deployment setting, where the model is going to be used for the downstream optimization tasks. Those are the routing and speed optimization that Antonis mentioned, the deepSea project, and the vessel performance optimization. Okay, so this is a typical pipeline, and in the following slides, we're going to cover some concepts that mainly refer to the data, the modeling, and the evaluation steps of this pipeline. So to begin with, let's state two facts. We are working with data that are non-stationary, and we do know that we have biases in the data. We have, for instance, underrepresented states, and we also have spurious correlations. So let me give you an example of a spurious correlation that I think is very easy to understand. For instance, assume that we are in a situation where we have bad weather. So what typically a captain will decide to do is to decrease the speed of the vessel in such a situation for safety reasons. Okay, so we do have these problems in the data. And the second fact now is that if we follow the standard train and test splitting, then this process suffers from the same biases. The thing is that you end up with a train and a test set that they both come from the same distribution. Therefore, they both have the same biases inherently to them. And when you try to evaluate the performance of the model using the test data, then you end up with generalization metrics that are also biased. Therefore, they're not indicative about the performance of the model in the deployment setting. So in the aspect of explainable AI, what we proposed at this point was to move to the synthetic domain, because by its construction, the synthetic domain is deterministic. So in this case, we can construct additional test sets that we can ensure they are unbiased. Therefore, the metrics that we're going to calculate in these test sets are going to be universal and robust. Okay, so here let's see very briefly how we construct a synthetic data set. What we do is that we use an analytical physics-based generator model, the J function, and we take the real signals coming from a vessel in order to produce the synthetic power through the generator. So essentially what we do is that we keep the real signals and we replace the power labels with the synthetic power labels in order to end up with a synthetic data set to work with. An additional step here is to add noise to the synthetic power in order to get the final synthetic power labels. And we do that in order to bring the synthetic data closer to reality, so as the data set to be more challenging for the model. Okay, so this is how we construct the synthetic data. And let's see now why doing so has advantages. So as I said, since we have moved to the synthetic domain, we have the data generator, the J function. And the true advantage of this is during the evaluation of the model. We can utilize this generator. For instance, in the simulate scenarios, we can simulate what if scenarios we want, and we can always compare with the ground truth as produced by the generator. The second thing that we proposed is to work with a so-called generalization set. This is an additional test set that is very big in size, and the way it is constructed ensures that it covers the convex hull of all possible feature combinations. Also, for the input features here, we have done an IID sampling. Therefore, we have broken all the spurious correlations that we had present in the synthetic data. And because of these properties, we can investigate and assess the true generalization capability of the model. And also we can research model properties like the causal disentanglement that we are interested in. Of course, yeah, these are very big advantages that have helped us to develop and research new models, but there are also some limitations we need to speak about. Okay, so the generator is a simplified version of reality. And this is because the analytical functions, while they are very good at reproducing the calm weather scenarios, we know that they fail to model accurately the bad weather scenarios. So, but still, the synthetic domain is a suitable region where you can research new methods. Unfortunately, though, because of this limitation, we cannot apply the models to the real deployment setting. And this is why, when we are done with working with the synthetic domain, we need to transfer the model into the real data and validate its performance there. So a question here arises, and this is how we can do that. As we said a bit earlier, is that the standard train test splitting suffers from data biases. And here, what we decided to do for the real data is to use a more advanced splitting. The idea is to perform a canonical dataset splitting that is suitable for the systematic application of the robustness of a model to the distributional shifts that we know, of course, that the data that we're working with suffer from. So in this case, we were driven by the business of the problem, and we decided to split the data set, as shown here in the illustration, using 2 dimensions. So the first dimension is the time, because we need to take into account the non-stationary effect due to the fouling of the hull of the vessel. And the second dimension is the wind speed that serves as a proxy for the weather effects. Therefore, the way to split the data can expose the model performance of the bad weather that we are very interested, because the business is very interested on this particular region of data, especially for the optimization tasks. So we split the data in the way that you see here, and what we can do with that is that we can attribute the performance of the model to certain partitions of the feature space and expose how well it does it, both to data that's showed during training, but also to unseen conditions. For instance, here in this red box, here you see data that are kept hidden during training, and these data are the most recent in time, and they also have the worst weather conditions encountered in the dataset. So this is a region of data that we are very interested in about the performance of the model. The third concept I want to discuss refers to the modeling step. So taking into account the downstream tasks, we have specific properties that we want from a model. We need to have robust power predictions, for sure. And we need the model to generalize well enough on unseen conditions. An additional thing, especially important for the downstream task, would be if we can somehow get an estimate about the confidence of the model for its predictions. And the way to do this is to use the predictive uncertainty. So a few words about the uncertainty. Uncertainty has 2 types. The first one is called aleatoric uncertainty, And what it actually quantifies and is the variance of the data because of the stochastic nature of the collection process. And this type of uncertainty is irreducible. The second type of uncertainty is the epistemic one. This uncertainty refers to the uncertainty of the model parameters. And this is the type of uncertainty that can be reduced. So, for instance, one could gather more data in order to reduce this uncertainty. So in this case, what we need is more data that cover a wider region of the feature space, or, for instance, fill in possible gaps that you have in the given dataset. Okay, and why this concept of predictive uncertainty falls into explainable AI? Uncertainty is a concept that the humans can easily understand because we are familiar with this concept and we use it in our everyday life. So we can use uncertainty in order to build trust with the stakeholders. And as I said a bit earlier, we can use uncertainty as an input to the downstream tasks to improve them. So a lot of benefits here. And let's see a method that we use that can provide us with predictive uncertainty. This is the probabilistic neural networks. So what such a model does is it learns a distribution on its point of prediction. So assuming that, for instance, the Gaussian distribution shown here is a good approximation for the target distribution, then what one needs to do is, if, for instance, it works with a regular DNN structure, what one needs to do is to replace the output layer with a two-node output layer. So in this case, the two nodes represent the two parameters that define the Gaussian distribution. And particularly, the first one, the mean of the distribution, what it actually gives us is the expected value for the prediction of the target, which is the power in our case. And the second parameter, the standard deviation, actually quantifies the variance inherent in the data. And this is why it is stated that the standard deviation of this Gaussian distribution is a quantification of the aleatoric uncertainty. Okay, so this is good news, right? By using the probabilistic neural networks, you can get an estimation about the aleatoric part of uncertainty. What about the epistemic part? So yes, you can do it, you can get that as well if you use the ensembling technique. So if you use ensembles of probabilistic neural networks instead of one probabilistic neural network, then you can get estimations for both types of uncertainty. And this is the maximum information you can get out of this method. Okay, so at this point, excuse me, okay, so let's move on a bit more. So we're going to focus on the probabilistic models, and we're going now to see some outputs from this type of models. So in this case, we're going to see a calm weather simulation. This is a condition that was present in the trained data that was used for this model. And I want also to tell you that we are going to work with a synthetic domain, and there is a reason for that. Okay, so let's see what a typical simulation output looks like from such a model. So this is the result. So what we see here is the estimated average trend as given by the model. This is the solid black curve. And we also have the estimation of the uncertainty. The thing is that since we are working in the synthetic domain, we have another tool on our hands, and that's it, the data generator. So we can use the generator in order to produce the ground truth trend, right, in the same conditions. So this is here. So what we see here is the result from the generator. And here we have again the ground truth trend shown by the cyan curve. And we also have the data points in the background that were produced by injecting a specific noise pattern in the data. So here the idea is to take these two, compile them into a single plot and do direct comparison. So what we can say here is that if we compare the ground truth and the estimated trend, which are the two solid lines, we see that they are in a very good agreement, while in the majority of the speeds, but they start to diverge at the high end of the speeds. So this region here that we see some divergence is actually an extrapolated region. And the second thing that we can observe in this plot is that the noise in the data follows a specific pattern that is very similar to the one estimated by the uncertainty that we see through the dashed lines. So the uncertainty estimation of the model is very accurate in this case, since it follows the same pattern. So this is good news, actually, for the model. Okay, you can do one more step here. You can also decouple the uncertainty estimation into its two components. And this is what you can see in this plot. Here we can see both the epistemic part and the aleatoric part and how they behave in the range of speeds that we examine. And let's discuss a bit why such a result is important for us. So first of all, by producing such a result, such a visualization, we can communicate the information that we can get from the model. We can depict the model confidence around the estimated trend, which is very valuable and easily understood by the stakeholders. Using this type of simulations, we can also explore various what-if scenarios. And we can do that in order to expose the regions of failure, if present for a model. So let me give you one more result in another what-if scenario here. In this case, we are going to simulate the bad weather case. And specifically, the case that we present here was not present during the model training. So we are in an extrapolated region. So if we focus in the center plot here, what we can see is that, yes, the two solid curves are still in very good agreement, but for the high speeds, we have a divergence that is more prominent than the previous case. And on the other hand, if we focus on the uncertainty part, keep in mind again that we are in an extrapolated region, and the estimation of uncertainty is still very informative, since it follows a pattern that is very close to the noise that was injected in the data. So this is a very good characteristic for the model, and therefore it again is a success story. It passes the evaluation, since we can use this uncertainty in the downstream tasks. Okay, so that was the third concept. Let's see now a bit about the metrics, because we still need metrics apart from qualitative tools to evaluate the model. So again, for models that can output both a prediction about the target and the uncertainty, still we can use the standard errors. Of course, we are all familiar with in order to address the predicted performance of a model, but there are also other types of models stated in the literature that can jointly assess both the robustness of a model and the quality of the uncertainty estimations. Here, the idea is that this type of metrics, what they essentially quantify is the degree of correlation between the errors of the model and the uncertainty estimations. So a very good model, or even the optimal case scenario, would to have 100% of correlation, meaning that the higher the model, the higher the uncertainty estimation. So this is the basic concept of these metrics. I'm not going to go into detail about this, but at the bottom of the slide, you can see the paper that we're based on. So for more details, you can go there. And that was it, I think. Yes. So at this point, let me do a summary. What we saw was 3 different concepts. The first one was about the synthetic domain evaluation. And this concept, what it tells us is a way to evaluate the models in a more rigorous way and be able to research new methods there and select the most promising models. The second concept was the canonical partitioning that you can do in the real data in order to evaluate the real performance of the models. And the partitioning that we showed you is dedicated for the investigation of the distributional shift robustness of the model. The third concept was about the probabilistic neural networks that can output, apart from the prediction, an uncertainty estimation. So at this point, we take all these 3 concepts, we combine them, and this is how we end up with our contribution to the SIFS project. Okay, so very few words about the SIFS project in general. This is an international collaboration between universities and the industry. And this project aims to study the distributional shift in machine learning for real-world applications. So within this project, a few months ago, we launched the Shift Challenge. So this challenge is about 2 tracks. The first one is the white matter multiple sclerosis lesion segmentation, which is a very interesting project, in fact. And the second track is the vessel power estimation. This is our track. So here, what we ask the participants to do is to follow our evaluation benchmark protocol. In this case, we have 2 phases. The first one refers to the synthetic data. The participants are going to use the synthetic data in order to develop models and select the most promising ones. And during the second phase, they're going to take those candidate models and they are going to train them and evaluate them on the real data. So eventually, they're going to take a rank on the leaderboard, and the top 3 participants will get a prize out of this. We are very happy to be part of the SIFT Challenge and the SIFT project in general, and everyone is welcome to join this challenge. It's a very interesting topic. Here are some useful links about this project. For instance, we give you the website of this project. There is also a link about the competition that is currently running. Everything that we present in this competition, all the code that we have used is publicly available through the GitHub repo. And of course, the data that participants are going to use are publicly available through Zenodo. And at the bottom, we have 2 papers, 2 of our papers that cover the topics that we have presented here today. So anyone who's interested can go there to check more details about what we discussed. So this is it. And last but not least, let me present the AI team of deepSea. So these are the people who are behind all the great stuff we're doing. So yeah, thank you all for your attention. That was it.
Thank you,
Efi.
Thank you, Efi. Thank you. I don't know, do you have still some slides or are we?
No, I think we finished. We can have a discussion or answer some questions.
Thank you both. Thank you both. It was really interesting, and you left quite a bit of time for discussion, which is good. Thank you for that. So I'm gonna check if there are any comments. Anybody who wants to ask a question can either raise their hands or probably easier to just type in the chat. Typing the question in the chat, we will all be seeing that. Are there any questions before I start shooting mine? No. No. Yeah, sorry, there is a question from Dimitris. Okay. It's about the potential combination of the two different types of uncertainty. Can we?
Yes. Yes. The question is on how we use them. If you use them combined or separately, it basically depends on the task. It depends on first and foremost, we have to understand that some of those plots are directly visualized for the user. So the first use of such information can be directly understood by the user. So in that case, we can use them separately. So as Efi showed us before. So yes, I think it depends on the task. I wouldn't say both of those they measure different things. So it's not a matter if we use one or the other. Each one carries a different kind, let's say, of information. But for the user, we should present them separately, I would say.
Thank you. Any other question? Maybe I will ask one of mine, and then if somebody wants to write something, they can. You mentioned a very interesting approach to splitting of training and test data and validation, which is something that we also frequently come across, and there is also some literature, especially regarding data that is streaming in some sense, that comes over time. It was not very clear to me what is happening over time. So I saw there was a temporal split of the training and the test data.
Yes.
But what happens across time? Is there a shift? Or...
Yes, I think, can you move to that slide? Yes, as very briefly touch upon it, there is a natural phenomenon in shipping, in vessels, which is the hull fouling. This means, it means basically that your resistance increases over time. And it's very expensive to directly measure it because you have to send someone to check it. And still you cannot measure it in terms of resistive force, for example. It's even more difficult to do that. So you know that this is happening, and it can be observed as a distributional shift. So the observation is the distributional shift. And we still have to model it, okay, through time. And this is a way how we test it, let's say. So we have to partition the data in a meaningful way that serves the business, serve this need to see if we are modeling correctly. So that's why it makes sense to split across those two dimensions. The first dimension is time, and the second dimension is weather, because wind, basically, which is a proxy for bad weather, because when we're dealing with vessels, you very much interested how well you predict in good and bad weather conditions. You need to know that. So yes, that's the idea behind it.
That is clear. My question was a bit different. My question is, if this is, I mean, presumably you have a stream of data. So you have data that continuously grows, if you want, across time.
Yes.
So once, at a certain point in time, you have a particular piece of this data available, and you split it into training and test, using the most recent part as the test data. But what happens next? So what happens when new data comes in? Do you shift the training set, or do you increase the training set? And use
okay. Yes. Okay. This is okay. I think the question is how we assure that our models are adapted properly because of this phenomenon. How we extend, how we extend our training set. Yes, we try to use all the data, all the available data, in order to be sure that we properly model this phenomenon. So yes, that's what we're doing. Now, if we want to evaluate the model, like in this case, we have to leave something out. But again, you cannot. Okay, I'm going to go very technical here. It's not only the fouling, but it's also how when you clean the vessel. So this additional information. So you cannot use only time. You have to use also additional events, let's say. So yes, you have to, in your data set, you have to have both. And yes, the question is still how you extrapolate time. That's my
the main question is whether the main question really here is whether drift is affecting you. So whether old data is contaminating your training set, and the fact that you do have events that change the situation, so that you have drastic changes of the distribution because of external events like cleaning, makes it more complicated. I don't want to monopolize the discussion though, because there are already a couple of other people.
A long story short, I would say that we convert the problem from a non-stationary problem to a stationary problem. That's how we deal it. So this drift is a real thing, but we nevertheless we address it. We put all the available information and time, and basically we transform it to a stationary problem. And that's how we can train models, basically. But we still have to test it if the modeling is correct. So yes, we transform the problem from a non-stationary to stationary. That's the short answer to it.
Thank you. As I said, there are a few questions waiting, so I will pass on. I think the first one who was Dimitris Voyagis, who raised his hand. Dimitri, do you want to ask the question? Can Dimitris?
Yes, please.
Hello. Hello, can you hear me?
Yes.
Okay. Thanks for the talk. I cannot activate my camera for some reason. I got disconnected for a couple of minutes, so maybe my question is something that you mentioned, but I missed it. My question concerns the synthetic data and the function that you've got to create the synthetic data, the model, if you like, that you've got to create the synthetic data. Let's say the G function. The question is, I mean, how much you trust this model? I mean, is it something provided by naval engineers? Whether there are some thoughts about being adequate? I mean,
yes, this is a really good question. Because if we were sure that this Z function, if we knew this Z function, basically we wouldn't need any further model. That would be adequate. But of course, this Z function is limited. It comes from naval engineering, from known physics, well-established knowledge, and we develop it as we advance it, and we develop it as we develop our models. So we try to make it as much complicated and representative to the real world. So again, we cannot be sure, but this is the best we can do. And that's why we limit this method to assess models during research. We cannot transfer it to the real world because there we use only data. And that's the idea. Yeah. So yes, as we see those two proposals, those two concepts, they serve again a different purpose. So we use the synthetic world, the synthetic domain, to research new models, and we have strong evidence, and we have measurable let's say, metrics that if you don't use it, you cannot distinguish performance between different models. You progress up to a point, and then you cannot go further because you're never sure if your data set is the problem or your model is the problem. So somehow you have to go further, and that's where synthetic domain comes into place. But still, this is a method that cannot be applied to the real world.
Okay, thanks.
There is a question from Dimitris Politikos about the connection between the data used for the synthetic data, the real data used for the synthetic data, and the model itself. I think there's a bit of confusion here about how the two work together. So Dimitris is asking whether there is some sort of oversampling, and how do you get the labels using?
Okay, if I understand correctly, we built this G function from the naval engineers that they assure that it can work to the whole space of possible conditions, and then we use a real data set, but we're using only the X part of it, not the Y part of it. So we forward pass our data set through this G function, and that's how we're keeping the original distribution of the data in terms of the X, but we are making synthetic labels out of it, so we know what is the ground truth basically, and then we can train on this. So we train on a data set that could be biased, right? But we know the ground truth. That's what we gain.
To put it differently, Antonis, if I'm not mistaken, what you do is that instead of using the simulator to generate randomly positions that together with the labels, you take real positions,
exactly, because we want to ingest all the biases, the selection biases, the spurious correlations the dataset has. We want to the model to ingest those, and nevertheless to see how it performs afterwards. So I think C2, the next slide is more. Yes, next slide, Efi.
There's a question from Stavros Niafas asking whether you have tried relational autoencoders to create synthetic data.
Yes, this is also a good question. I wouldn't think we have thought of it, but we don't think that it's going to give something new here, because we want to have the original distribution of X in order to, as I mentioned, to force the model to see only that data, because that's a real case scenario. And then we use the whole convex hull of the whole space basically, so we can reproduce the whole space through this G function. So basically, I don't see so far we haven't seen the value of remodeling, let's say, the generative distribution. Yes.
If I can add to that again, if you do have a physical model that is specific to the particular problem that you want to solve, everyone would usually prefer that to a generic approach like autoencoders, unless there is a way to combine both.
Yes, because yes, for us it's like sort of a ground truth. So we know all the assumptions we have put into that function. It's a very like interpretable, inspectable, something that we have built, right? And then we can test all those biases we mentioned. Like as you see here, we still train on the training set that we would have from the real data set, but the labels are synthetic. So if there is a spurious correlation there, the model has to address it. And then we test it on the red distribution, the test distribution, but also on the general, the complete convex hull of the feature space. which is sample IID, as Efi mentioned. So then there, basically, we can test the actual generalization performance. This is the whole space. There is nothing left out there. Of course, there is a question, as very correctly asked before, how do you know that your G can perform well in this space, across the space? We cannot be sure. That's the answer. Yes, but this is the best we can do, basically. Yeah, so when we test in the red distribution and also in the light green distribution, the complete space. And when you test it there, then your metrics, they're becoming universal and robust, because otherwise your metrics are not robust. Metrics that are bound to the distribution, the test distribution, the same, they are not robust. Although they are used widely in the industry, and they communicate it wrong. Everyone is claiming 99.9% accuracy. Yeah, fine, but your distribution is biased. So your real performance will be in the real world when you will have the light green distribution. You won't have the red distribution. So yeah, it's far more challenging when you have to simulate all possible conditions than working on a restricted data set, a given data set. So this is something very, very difficult to address. Yes.
I have a very simple question, which I missed from the presentation. Who is the user?
Yes, the users are basically the users we may have different kinds of users, the operators, the ship owners. Yes, this yes, different kinds of users.
Are they technical people or business people or both?
Both, yes. For example, when you maintain the vessel, your user, yes, is the owner of the vessel. Let's say the technical team of the owner. But when you are optimizing voyages, then the operators of the vessel are interested in optimizing the voyages, for example. But in any case, I'm not an expert in this, so yeah, this is a business question. But yes, again, we have different stakeholders.
But it does affect explainability and interpretability a lot to know who the user is. Right?
Yes, that's why we're doing the best we can. Yes, we try to serve all of the possible stakeholders. That's why we have paid so much attention to visualizations, to how we explain by simulation how our models work, because the plots you have seen before, the PV plots, as we call them, it's a standard method of communicating models across the industry. And we have to respect that and build on top of that. So one part of explainability, one goal of explainability is to be able to simulate in order to prove that you perform well. And this is something that the industry already has been doing, and we complement that. We're pushing it further. So we put uncertainty on top of it. We can simulate a broader range of conditions. Traditionally, the industry would be able to simulate only good weather conditions. Since we're data-driven, we ingest all possible data, and we can extrapolate to across the board, basically. Yes. So yeah, interpretability and simulatability is again two concepts that they go together.
Okay, there is one more question from Stavros Niafas. As a data science team, did you manage to figure out the correct KPIs, business KPIs, mapped with your model's performance?
Yes, this is a good question. If I understand correctly, is how you what is a good KPI to measure basically the performance of the end product, let's say, if that's the question. This is again, it falls into the informativeness aspect we mentioned. Like your metrics, basically they don't measure how well you're going to do in your downstream task, and this is a real problem in the AI in general. So you measure mean square error, but the question is how well you perform the route optimization at the end of the day. So there is a significant gap between what you measure when you're optimizing your model and how your task is going to be measured after you deploy it. So I think this is an open question, and the way we try to tackle it, because of course you cannot directly optimize for your KPIs, is to develop a very powerful simulation framework. So basically, we can train models, deploy the models in the downstream task, and run simulations. And in this way, we can determine which model performs best on the downstream task. I think this is, sometimes this is the best you can do. You cannot directly optimize your KPIs. This is very difficult to do. But you can test your most prominent hypothesis and see what performs better. Yes, so that's a really good question. Like your optimization metric is not a good proxy for your KPIs. Yeah.
Okay. I think we have been running a bit over time. Thank you so much for that. I think we had a very interesting discussion. I'm really happy to hear about what you're doing, and it's really interesting. I hope we get also the chance at some point to work together. There's a lot of things that ring bells regarding the different teams working on in the lab for different directions. Thanks again. Thank you very much, and all the best in your work.
Thank you.
Thank you. Thank you.
Bye-bye.
Bye-bye. Thank you.
Bye.